SwayamPrabha. Digital India. Educated India.
Good afternoon. Today we will discuss about some other important aspects of flow modeling. We have already discussed a few. Some other aspects are to be covered today. But before starting the actual lesson for today, we will recapitulate what we did in the last class, some important points that we did in the last class. As we mentioned in the last class, that second upwind differencing is an improvement of first order upwind differencing, and this is built in with most of the popular codes that are in used, such as ANSYS Fluent, CFX, etc. So it is of interest to know about it. We have already seen what it is, but even then we'll just recapitulate again. Let us look at one-dimensional space defined by ij, I plus 1j, I plus 2j in one direction, another direction I minus 1j, I minus 2j. And UR is the point which is at the right hand side of ij. UL is the point which is at the left hand side of ij. UR is defined by equation 2, UR and UL definition we can get here. This is exactly midway between UI and I plus 1 comma j in the eastern direction or in the right direction, and in the left direction or west direction it is again exactly half between I minus 1j and ij, and we are saying UL is located here and defined here, and UR is defined here, and U is the carrier velocity. It is transporting maybe velocity itself. It may transport temperature, it may transport concentration of a species. So basically it is U is the carrier velocity. Now also the basic principles of upwinding is, if UR is positive, then zeta, which is being transported, zeta R, will be at the upstream point. So here if UR is positive, then zeta will be defined at ij, zeta ij. If UR is negative, then zeta will be defined at I plus 1j. Similarly, if UL is positive, then zeta L will be defined at the upstream point, which is zeta I minus 1j. And if UL is negative, then zeta will be defined at point ij, rather downstream point, if UL is negative. Rather, I should say, then also it is upstream, because if UL is negative, then ij point is the upstream point with respect to negative velocity. And if UL is positive, then UI minus 1j is the upstream point. So here what we have done, we have we can see that del x of U zeta which is 1 by delta x, and then ur, we have associated zeta ij with that, which is at the upstream point, and ul, we have associated zeta I minus 1j with that. This is also zeta at the upstream point. So we have taken ur and ul, both are positive. We are doing our basic derivation based on that, but later we will see that our derivation would be such that even if we change the direction of ur and ul, the formulation will remain valid. So here, from the last expression, that means expression 5, what we have done, we have basically substituted this zeta ij by, since it is derivative of u velocity, uij minus again ul into ui minus 1j. Then what we have done, we have basically added with this uij, you can see in the bracket, ui plus 1j, and subtracted that. And so basically you have written uij plus ui plus 1j plus uij minus ui plus 1j. So if we really perform the algebra, this is nothing but uij. Uij we have written this way. Similarly, ui minus 1j we have written as ui minus 1j plus uij plus ui minus 1j minus uij by 2. And again, if we perform this algebra, we'll get back ui minus 1j. This is a sort of, rearrangement. Then we have, this 2 into 2 at the denominator. We have transferred to the to outside the bracket 1 by 4 delta x, and then we have tried to regroup the basically different bracketed terms. Here it is uij plus ui plus 1j. We have multiplied it with this, because it is multiplying this entire quantity. We have just grouped this. We have uij plus ui plus 1j plus uij minus ui plus 1j. The second term that means associated with ul. So here also uij plus ui minus 1j. This we have first, we are multiplying with the entire quantity defined at the numerator, but we have written ui minus 1 plus uij plus ui minus 1 minus uij. Idea is that, see, here we are getting basically square of uij plus ui plus 1j. You can see square, first multiplication. Second multiplication is given, it is like a plus b into a minus b, so a square minus b square. Then third multiplication, again ui minus 1j plus uij squared. Again the fourth term is a plus b being multiplied with a minus b, so ui minus 1j square minus uij square. And this way, writing this has some advantage. We'll be able to appreciate in the next slide. What we have done, that we have, in the next slide, we have retained this term, but this term we are writing as uij plus ui plus 1j multiplied by uij minus ui plus 1j. Again, a square minus b square is being again split as a plus b into a minus b. But while doing this, we are placing a modulus sign here. So this is modulus of this quantity. Similarly, if you go to the previous slide, we'll retain this term of equation 6, but this term a square minus b square will again split into a plus b into a minus b, a plus b into a minus b. But this time this term a plus b is under a modulus sign. Now this under a modulus sign we have placed strategically because this is basically defined at the right nodal point velocity u, and again at the left nodal point velocity L. This quantity ui minus 1 j plus uij at the ui, this is basically at the location L location ul. Now if ul is positive, based on that we derived it, it is valid. But if ul and ur, if these are negative, then also you will see this remains valid, because even if it is negative, it will assume the modulus sign and calculation will remain same. So now we are introducing this modulus sign in order to have locally ur and ul be flexible. This can be positive as well as negative. ul can be positive as well as negative. And then we have also introduced one symbol eta. Eta is basically between, we have written here, eta varies between 0 and 1. If you place eta equal to 0, you can see this whole differencing del del x of u square will be u at r point squared minus u at L point squared. So this is basically central differencing. And if eta is 1, then you will see this will be basically first order upwind differencing. So we will vary eta between 0 and 1. Preferably eta should be kept as low as possible. Why I am saying as low as possible? Because presence of eta is needed. This will give the upwind bias. Upwind bias is needed for retaining transportive property and making the formulation such that it never violates transportive property. But if upwind is done in such a way that it increases artificial viscosity, then we are introducing some error. We have learned about artificial viscosity, relationship between upwinding and artificial viscosity. So more contribution from upwinding will increase the artificial viscosity more. That is why eta is needed, but it should be as minimum as possible. It should just maintain good enough to, it should be good enough to maintain transportive property. But at any point of time, it should not contribute to large artificial viscosity or significant amount of false diffusion. So usually, while working with a scheme, some trial run is given, but it is preferable to retain this eta value somewhere near 0.2, maybe 0.23, 0.24, etc. It is tested that serves a purpose. Now we will, based on this, we will start our today's discussion on even higher order upwinding scheme. So this is a very well-known higher order upwinding scheme, which is known as third order upwind differencing of, we have written here the name of the first author, Kawamura, second author is Kuwahara, There is a third author also, Takami. So, but all of them worked with Professor Kuwahara. Professor Kuwahara at that time, he was in Tokyo Institute of Technology. He's a very well-known fluid dynamicist. And this scheme was devised by him. He devised this scheme to solve the turbulent flow problem. As such, he attempted direct numerical simulation using this scheme so that false diffusion is almost neglected or zero, and other form of discretization errors are also minimized. You can see this is third order upwind differencing. So basically second order error, which gives the first leading term of artificial viscosity, new artificial into del 2u del x2, that new artificial will not be generated. It will have even higher order errors, maybe fourth order, fifth order errors, which are, basically dispersion error, phase error. Those errors may be introduced, but if the finer grid is taken, those error also will be minimized, but second order error is not there. This is third order accurate scheme, and I have written it only in one dimension, so you can see how it has been written, and it has involved I plus 2, I plus 1, I minus 1, I minus 2, and obviously ij point. So ij point, and on either side 2 points. So this is called 5-point stencil. So in order to find out derivative at a point, you need, in one direction, you need 2 points in the downstream direction, 2 points in the upstream direction, and it's called 5-point stencil. And here also you can see this uij is placed under modulus sign so that it can handle positive u or negative u at the point of interest at the ij point. The expression will eventually be valid. Now again, let me remind that this has been done in one direction, and the model discretization on one-dimensional paradigm. In three-dimensional paradigm, these terms will be little more complex because no quantity is one-dimensional quantity in three-dimensional paradigm. So very interesting discussions are available. I have given some references, Professor Bhanka's reference, Professor Fletcher's reference, and another reference, Rai and Moin. We will discuss about that scheme also in the next slide. So next slide, since we are now discussing higher order discretization schemes, we will discuss a very popular scheme which was developed by Professor Leonard in 1979. This is called QUIC scheme. QUIC is acronym. It means quadratic upwind interpolation of convective kinematics. And you can see here also QUIC scheme involves point of interest, that means I, and then the upstream points I minus 1, I minus 2, downstream points I plus 1, I plus 2. So this is also based on 5-point stencil. And here also you can see here this Fi has been put under modulus sign in order to take care of the sign of F. We have given deliberately F, so it was written that way. So F is basically the velocity of interest. It is ui in our case, and sign of ui, whether it is positive or negative, we will place it here and it will eventually take the correct form. This scheme, quick scheme, is a very popular scheme, and this is also available in most of the commercial codes. Next scheme what I will mention, this is not available in any of the commercial codes. This is again developed by Stanford Group. Or many of you might be knowing a very famous place in Stanford University called Center for Turbulence Research. There, Professor Parvez Main and M.M. Roy, they developed this scheme in 1991. And this is for doing direct numerical simulation. Now, a side remarks is that although Professor Kuhara also developed this scheme for doing direct numerical simulation, Quick was also developed with the basic target of doing direct numerical simulation. Direct numerical simulation we'll discuss later little more detail, where you do not use any model for turbulence modeling. You take very fine grid and you basically use the numerical scheme which produces absolutely no error. And the grid size is such that it is below the smallest fluctuation, smallest turbulence fluctuation, which is known as Kolmogorov scale. So if you want to go for such fine grid size, maybe for a given domain, you may require 10 to the power 12, 10 to the power 14 grid points. And obviously, in 3 dimension with so many variables and with 10 to the power 12 or 10 to the power 14 grids, you cannot solve using ordinary computers. The program has to be parallel program, and it has to run on basically supercomputers. High performance computing platform is needed for that. So target was to address DNS, but in practice today, I mean, again, this is a passive remark. This Professor Kuhara's third order upwinding or quick scheme, these are used for very accurate simulations, but not for DNS. They are used for another very accurate turbulent flow simulation technique called LES, large eddy simulation, and several other intricate flow problems where very high level of accuracy of discretization is needed. These two schemes, Quick and Professor Kuhara scheme, is called third order Kuhara scheme. These are both used for all such purposes, but for DNS, its acceptability is not that much. We do not have the right time to discuss all those issues. I will just mention what happens in practice. Now I will remark on Ryan-Moyne scheme. Ryan-Moyne scheme is a scheme which is used for DNS calculation. Very popular scheme, and basically another such scheme is called Lilly's compact scheme. That is also very accurate, used for the purpose of DNS, and was developed by Professor Sanjeeva Lele in again Stanford. And this is Ryan-Moyne scheme we are mentioning here. Here also you can see that it is fifth order accurate. Formally, Quick and Kuhara's third order scheme, name itself is saying these two schemes are formally third order accurate, but Ryan-Moyne scheme is fifth order accurate, and it involves, you can see, 7 points. I is the point of interest. These are downstream points. I plus 1, I plus 2, and I plus 3. These are downstream points. And these are upstream points. I minus 1, I minus 2, and I minus 3. So I minus 1, I minus 2, I minus 3. 3 upstream points, 3 downstream points, and the point of interest. 7 points are needed for this accurate discretization, and this is called 7-point stencil. This A phi, again you have this is a carrier phase velocity. You have seen that we have put it under modulus sign, and that means it can handle whether locally the velocity is positive or negative. That doesn't matter. This alpha is a factor. It can be varied. Usually it is 1, but it can be made more than 1 also. It takes slightly different form, but usually alpha equal to 1 works well. Now I will wrap up this accuracy related discussions. We have only discussed about formal accuracy of convective terms, specifically one convective term. This way other convective terms can be discretized following higher order discretization method. But accuracy means something else. It is a combined aspect. So it is accuracy of convective terms, accuracy of discretization of diffusive term, then accuracy of grid related error, whether grid is fine enough, whether grid is skewed, or grid related errors are dominating, and then temporal discretization. Usual temporal discretization we have mentioned here is a first order discretization, whether ui or uij or uijk at n plus 1th level minus ui or uij or uijk at nth level by delta t. So we have seen also in last lecture that from the truncated terms of discretization error, second order error can come. So therefore there are ways to have higher order temporal discretization. These are called Adam-Bashforth scheme. Runge-Kutta schemes are also used for progressing in the time direction and maintaining higher order accuracy. But all these are basically needed. Such a high level of accuracy is basically needed where flow with very high level of accuracy, as I said, that the smallest fluctuation of turbulence or similar such accuracy is needed. Usually in engineering flows, such high level accuracy may not be needed, but it should be reasonably accurate. So you will see in most of the problems, we'll try to go for higher order accurate scheme, preferably a second order discretization scheme of the convective term, or second and diffusive terms are usually second order discretization method is followed for diffusive terms, and the temporal discretization in some cases we go for second order accurate by adopting Adam-Bashforth method, and we also pay attention to the implementation of the boundary conditions very accurately. Having done that, we will just try to wrap up finite difference based nuances of discretization technique, because these are some of the aspects one should know before handling a flow and heat transfer problem. Now we will just touch upon a problem. We have given a heading, non-trivial problems with discretized equation. Now you can see equation 1 is Burger's equation. We have discretized the temporal term, forward in time, first order forward in time. The convective term, u del u del x, we have discretized using central difference, and diffusive term is obviously we have discretized using central difference. And then we have see if zeta I at n plus 1th level written in Taylor series in time direction, whatever expression we'll get from there, zeta I n plus 1 minus zeta I n divided by delta t, we'll try to regroup and see the remaining terms. Similarly, we'll perform this exercise for the convective term and the diffusive term. And if you recall, in last class we'll try to reconstruct the PD. And then here, as you can see, we have gotten back this PD, but this PD, instead of having nu into del 2 zeta del x2, it has nu minus u square delta t by 2 into del 2 zeta del x2. And this error is primarily coming from the temporal discretization scheme. Also, we have explained in the last class how the truncated terms of the temporal discretization can be expressed in terms of spatial discretization, the spatial variables. So it can be written this way. Now R is a quantity. We can define nu delta t by delta x square. C is u delta t by delta x. It is a Courant number, and this is called actually grid Fourier number, although we have not coined this term so far. Now for R equal to half and C equal to 1, we can see this equation, even though we are attempting to solve this equation will be completely, we'll be able to dispense with the viscous diffusion term completely. This will become an equation similar to Euler's equation. It is del zeta del t plus u del zeta del x equal to 0. Second thing is that if we substitute R equal to half and C equal to 1 at equation 1, let us multiply by delta t throughout, let us divide by delta x, and then we'll be able to get the, we'll try to write what is zeta I n plus 1. After doing that, we'll see straight away we'll get zeta I n plus 1 equal to zeta I minus 1. Straight away we'll get the solution. Zeta I n plus 1. Just do this faithfully. Transfer, keep the temporal term on the left hand side, transfer temporal derivative, transfer all other terms on the right hand side, then multiply whole equation, entire equation by delta t, and then divide basically the right hand side by delta x squared. You will see that right hand side, the term which came due to convective terms, you divide by delta x, which arises out of diffusive term, you divide by delta x squared. We have written here. So basically you transfer except for this temporal term, all other terms on the right hand side, and multiply by delta x. You will get basically zeta I n plus 1 equal to zeta I minus 1. So a solution is obtained. But this is not the solution, which is not acceptable. So in order to get physically meaningful solution, nu minus u square delta t by 2, this has to be greater than 0. This has to be a non-zero term. And zero term is extreme case. If we get zero term from there, it can be the Euler's equation. So combination is nu u square delta t by 2 must be greater than equal to 0. Now we can sort of regroup this u square delta t by 2 half u delta t by delta x into u delta t by nu. Then this is basically u delta t by delta x, nothing but Courant number. U delta x by nu is called Greed-Peclet number or Greed-Reynolds number. Different books use different terminology. Some books they call it Greed-Peclet number, Greed-Peclet number. Some books it is Greed-Reynolds number. Whatever it is, basically it is representative of Reynolds number based on the dimension of the grid. So from this identity we can see this equation, that nu into 1 minus half c into Re delta x greater than equal to 0. Nu is non-zero. From here we get Re delta x less than equal to 2 by c. Now in many places it is loosely told that Greed-Reynolds number or Greed-Peclet number should be less than 2, which is, we are also not violating that. We are saying it should be less than 2. So upper limit is 2, but actually it is less than equal to 2 by c, 2 by Courant number. Then depending on the value of the Courant number, this Greed-Peclet number, we can have a little more affordable value, because Greed-Peclet number is basically will define your grid density. Here it is in x direction. Similarly, it can be in y direction, it can be in z direction, or in r theta z coordinate. It will be basically in theta direction or in r direction. So whatever is the direction, in that direction, depending on the grid dimension, this is basically Greed-Reynolds number or Greed-Peclet number. And so grid density will dictate what is the value of the Greed-Peclet number or Greed-Reynolds number in the domain. And as I said, for getting a stable, meaningful calculation, the restriction is Greed-Reynolds number should be less than 2. But we have just modified it. Actually, Greed-Reynolds number is less than 2 by c. And since c is always less than 1, we can, get this, upper limit of Greed-Reynolds number more than 2. So it can exceed 2, but not more than 2 by c. So that's what we have written, that under such a restriction below Greed-Reynolds number 2, calculation is always stable. The interesting information is that it is possible to cross the Self-Reynolds number or Greed-Reynolds number of 2 if c is made less than unity. C is the Courant number. Now So far we have been discussing about uh, tridiagonal matrices. We have seen always our tendency was to formulate in such a way so that we can get tridiagonal matrix. Like in two-dimensional problems we discussed, we mentioned about ADI scheme, means alternating direction implicit scheme. In each alternating direction, we will get tridiagonal matrices. And why we are always trying to do that? Because it is very easy to solve tridiagonal matrix. If we get non-tridiagonal matrix, the solution is little more involved. As such, there is another similar such matrix which is called pentadiagonal matrix. There are certain algorithms which can solve also pentadiagonal matrix. I mean, not as easily as tridiagonal matrix, but though there are special techniques to solve pentadiagonal matrix also. Now, tridiagonal matrix algorithm is called Thomas algorithm, named after Thomas, who conceptualized it, because it's basically seeing something much beyond looking at a tridiagonal matrix. It was not otherwise possible to know that solution technique is so simple. So this algorithm takes advantage of tridiagonal Thomas algorithm. This takes advantage of tridiagonal matrix system. Gaussian matrix solver is applied to tridiagonal. Actually, Gaussian elimination method, which gives us of any arbitrary square matrix, gives us upper triangular matrix, and then solution becomes simple. Similar operations are done as such on tridiagonal matrix also. An algorithm is set by summarizing those operations. But final algorithm, when we get, it is very easy. So it transforms the coefficient matrix into upper triangular form. Then the solution is obtained by back substitution. So let us highlight the nomenclature. After getting the tridiagonal matrix, the tridiagonal system, coefficient matrix is given here. In the coefficient matrix, you can see we have not used ij indices. We have only used one index because we will just identify three diagonals. Principal diagonal, you can see he is having n number of elements, d1, d2, d3, d4 up to dn. And immediate the diagonal below it, you can call it subdiagonal, b2, b3, b4. One element will be one element will be less counted, so it is up to bn. B1 is not there. So B2, B3, B4 up to Bn. Again, in number of elements, one is less counted. So one less is counted. So Bn minus, basically n minus 1 elements. Similarly, A2, A1, A2, A3, A4, which is the diagonal at the above the principal diagonal. We can call it super diagonal also. 1, 2, 3, 4 up to an minus 1. So the A elements should have an array with dimension n minus 1. D elements should have an array with dimension n. B elements should have an array with dimension again n minus 1. And x1, x2, x3, x4 to xn, this x vector, column vector, these are all unknown elements. And right hand side, c1, c2, c3, c4 up to cn, again a column vector, and this of n number of elements are there. This is also known. So x1 to xn are unknown, all c's are known, all d's are known, all a's are known, all b's are known. We'll find out x1 to xn. Now it is this operation, as I said, it will be Gaussian elimination Gaussian elimination kind of operation, but it will finally transform coefficient matrix into an upper triangular matrix. So this is, in a way, we can call it LU decomposition. So LU decomposition can be viewed as the matrix form of Gaussian elimination. And see, in all this, what we will store is basically this D array, this elements, a changed D array, changed C array, nothing else will change. But as I said, behind all Gaussian elimination operations are on to convert the matrix into upper triangular matrix. But in order to know x1 to xn, we will just need diagonal elements of that upper triangular matrix and this C1 to Cn, this array. So changed array C1 to Cn, this has to be stored, and changed array D1 to Dn, these have to be stored. Other arrays will also be needed for starting the calculation. So we'll start the calculation with 4 arrays, D1 to Dn, A1 to An minus 1, and B2 to Bn. And the fourth array is C1 to Cn. And now we will change, with the help of the mathematical operation and B and A array, D array. And similarly, with the help of B and A array and the diagonal elements, will change C array. But storage of changed array, when we will consider, changed array will have only changed D array and changed C array. From there, we'll be able to get all the values of x1 to xn. Now, first we will show how this D array will change from D1 to Dn. Then we will show how C1 to C will change. So D1, you can see D1 new is D1 old. So first element of D1 array will not change. This will remain D1 old. But all other elements D2 to Dn will change. This is D1 new equal to D1 old minus Bi divided by Di minus 1 into ai minus 1 old. I is varied from 2 to n. So d2 new equal to d2 old minus b2 divided by d1 into a1 old. So this will be this minus then old value of d2 minus again b1. Now it will be needed basically b2 divided by d1 into a1. Similarly, d3 is new is d3 old minus here it will be b3 d2 into a2 old. So this way entire array d1 to dn will be changed. Now C array will also change. C1 new is C1 old minus again bi C1 new equal to C1 old. Sorry, so first value will not change. C1 new is C1 old. Now from C2, so Ci new equal to Ci old minus Bi divided by Di minus 1 Ci minus 1 old. That means I equal to 2 means C2 new equal to C2 old minus B2 divided by D1 into C1. So this way we will change all the elements here, and these two changed D and changed C are stored, and then we'll get back the values of x1 to xn. The system is LU decomposed. As we have modified the right hand side, all we need to do is to back substitution using U matrix, which is upper triangular matrix. Now this contains only A's. A's are there. A's we have not changed, and the modified diagonal. So now the new upper triangular matrix, effectively after doing Gaussian elimination operation, the new upper triangular matrix will have old A's and new D's and new C's. So the last term we can well imagine that it will be xn, and if these are all 0, so change dn and change cn. So xn will be that change new cn by dn, and then we can set xk equal to ck minus ak xk plus 1 by dk, and k will vary from n minus 1. This is back substitution. So first term is xn, second term is xn minus 1, that will be c n minus 1 minus a n minus 1 into xn. Xn has been just found out, divided by d n minus 1, because now just dn minus 1 or xn minus 1 cn minus 1, these terms are involved. So we will find out xn minus 1 from this expression, then xn minus 2, xn minus 3 up to x1. So x1 to xn, all the terms will be evaluated. So, and now all of us can appreciate why we go always after tridiagonal matrix algorithm, because it is entire system of tridiagonal matrix where the coefficient matrix is having only the diagonal element, and one diagonal below the diagonal element, another diagonal above the diagonal element. All other elements are 0. Then the x vector, which is unknown vector, equal to the c vector, which is known vector. And when we change this, the new elements, all c new elements are found out, all d diagonal elements are found out, and immediate super diagonal elements, elements above the diagonal a's, are not changed at all and need not be stored because this was stored earlier. So only D and C's are new values. A new array has to be there to store these values, and from there, making use of old A values, this new D values and new C values, we will be able to find out all unknown quantities. So we have discussed various discretization schemes applied to governing differential equations. Using discretization schemes and the solution algorithms discussed above, we can obtain the values of the dependent variables at the grid points in the domain of interest. That is what is our target. We have made ourselves acquainted with this knowledge, how to do that from fundamentals, and we'll apply that for more complex problems. Now, consistency, stability, conservative property, transportive property of the methods have to be looked into and have to be looked in detail before applying the solution strategies to a given problem. Obviously, we have seen these are very important issues. Otherwise, by violating these issues, we may not get the appropriate solution. Even if we get the solution, results are spurious. Many a times, the program will not work, it will break. So consistency, stability, conservative property, transportive property, these are to be really handled with care. Artificial viscosity is a parameter of paramount interest. It has to be there so that the algorithm works, but it should be minimized so that it is, not a disturbance to the numerical values of the dependent variable or its distribution of the dependent variables in the domain. So while discussing our lessons, we have taken help from several literature, open literature, which are available. I have just given a list so that when you prepare your lessons, you can always refer to these papers. I have mentioned it here. You can, if needed, you can download it from the respective journals on the net. All these journals are subscribed by IIT Kanpur, so it will not be a problem. Another point, while discussing about algorithms, our assignments, numerical assignments, finally you have to solve the problems using computer. So you have to write your own codes, and my suggestion is that whatever language you know, you use that language. Somebody knows maybe Fortran 77, somebody knows Fortran 90, somebody knows Fortran 95. All these are scientific languages you can use. Somebody knows C, somebody knows C++ well. So please use C, C++. Somebody, maybe enthusiastic about Python, so you can use Python. So any language please feel free to use the language. Only thing, depending on the computer you are using, you check it whether your computer is having that compiler. If your computer is endowed with C, C++, Python, Fortran, all these compilers, then use any language you like, because when I will look at the solutions that you have done, I will suggest you to run the codes, and the code should run and at least produce some sample results. Now we have given one example problem. This example problem we will discuss very quickly how to really formulate a given problem. So basically you can read it slowly. I will try to read it little fast. That this is a slab and we are solving a one-dimensional problem. This is the flow direction, x direction, not flow direction, x direction, and we are solving a problem which is dependent on x, because z direction, which is perpendicular to the plane of interest, is infinite and problem is not changing in that direction. Also y direction, which is perpendicular to x direction, in that direction also problem description is not changing. So the way, basically temperature, this is a problem. So this is a slab. This physical domain is a slab which is which has very large z dimension, that is dimension perpendicular to the plane, and again which is again very large dimension perpendicular to x line. So whatever variation is observable, that is changing only in x direction. It is repeating in all y's, it is repeating in all z's. That is why this is one-dimensional problem. So this is a slab of a nuclear reactor, and at the left hand side you can see some heat flux is coming, and which is quite high, 3 into 10 to the power 5 watt per meter square. This slab is exposed to that amount of thermal energy. So obviously thermal energy, and this slab is a metallic slab made of copper. So this slab will be heated, and some time has been given. After that time instant, you can see that consider a thick copper slab that is working as a wall of a nuclear reactor. The slab is initially at a temperature 35 degrees. As the reaction starts, slab is exposed to a heat flux of 3 into 10 to the power 5 watt per meter square. Using a strong implicit method, we have learned Crank-Nicolson implicit method. Here in the example problem, we will do another variant, also implicit but strongly implicit method, and with a space increment of delta x equal to 25 millimeter. Determine the temperature distribution up to the interior point, which is 150 millimeter away from the surface after 25 seconds. So initially the entire slab is having 35 degree temperature centigrade, and it is exposed to big thermal flux, and then after basically 25 seconds we have to find out temperature distribution in the x direction, and that temperature distribution is valid in all y, all z. So formulate the problem by writing algebraic equations and forming the matrix. One of the boundary conditions of the problem is given by the node next to the node 150 millimeter. So each node is separated by 25 millimeter. So the last node is basically what is being said, that after 25 seconds last node temperature will not change. One of the boundary conditions of problem is given by node next to 150 millimeter. So this is 25, 25, 50, 25, 75, 25, 100, 25, 100, 25, 25, again 150, maybe equal 25 millimeter away. Had there been a node 8, that temperature at that 8th node is not changing. So that is after 25 seconds. That is one boundary condition known to you. And also the at node number 1, the basically boundary condition is not known, but that has to be found out from this energy balance equation. This is basically accumulation of energy within this control volume. If we take a small control volume comprising of delta x by 2 in x direction, and maybe unit dimension is y and unit dimension in z direction, then that is the thermal energy, and this is the thermal energy going out, and this is the thermal energy coming in. So in above equation, V is the V with a cut mark, this is the volume, A is the area, and Q dot is the incoming heat flux. All other interior nodes can be calculated by using unsteady one-dimensional heat conduction equation. For the compactness of the equation, substitute AF as the grid Fourier number. Compactness, there should not be any gap. This is somehow typographical mistake. So alpha delta T by delta x square, wherever we will get, we will substitute that by F. Now let us formulate the problem. So basically this is the governing equation, one-dimensional heat conduction equation, del temperature del time equal to alpha del to temperature del x2. And for first node is boundary condition, we will determine it. Last node is also boundary condition, we will determine it separately. But all intermediate nodes, this equation is applicable, where we can write Tin plus 1 minus Tin by delta T equal to alpha Ti plus 1 minus twice Ti plus Ti minus 1, central difference. But we are writing all this at n plus 1th level. And we could have written Frank-Nicholson, then we had to write Ti plus 1 n plus 1 plus Ti plus 1 n minus twice Ti n plus 1 plus minus twice Ti n plus Ti minus 1 n plus 1 plus Ti minus 1 n by 2. So average of 2 time level we could have written. Then also we would have gotten unknown terms on the right hand side. But here we are writing directly at n plus 1th level, so that from here also we can formulate the problem. Now next step, you can see we have transferred delta T on right hand side divided by delta x square. This is F. So we can write the equation. We have brought all the n plus 1th level times on the left hand side, minus F Ti minus 1 at n plus 1 plus 1 plus twice F Ti n plus 1 minus F Ti plus 1, this term n plus 1 equal to only Ti at n is known. And we can substitute here I equal to 2, 2I equal to maybe 7. I equal to 2 means then it will be expressed in terms of T1 and T3, T2 will be expressed. I equal to 3 means T3 will be expressed in terms of T2 and T4. I equal to 4 means it will be expressed in terms of 3 and 5. So this way I equal to 5 means it will be expressed in terms of 4 and 6. I equal to 6 will be expressed in terms of 5 and 7. 7 will be expressed in terms of 6 and 8. So we will get these 6 equations straight away, but we have to now implement the boundary condition. First boundary condition is very simple, because see, we have written here T8, but T8 is not, within the domain. It is falling outside the domain. But we'll use that information on T8 as the boundary condition. It has been told that after this elapsed time, that means after 25 seconds, this temperature will remain at the initial temperature. So T8 is known, which will remain as the initial temperature. So we will write the last equation as this was minus f T6 n plus 1 plus 1 plus twice f T7 n plus 1. This is now f T8 is behaving as T7 of the previous level. So we will just substitute that. It is we are transferring this as T8 at nth level. We are transferring to the known side. So left hand side, unknown side, we will be left with this term and this term. This is known term, now transferred to the right hand side. Now what we'll do, we'll apply this equation, that means the thermal energy balance equation at this node. So energy coming in, energy going out through conduction, and the energy that is heating up this volume, the thermal energy contained in this volume. So simply we have written that part. So this is delta x by 2 is the dimension in x direction. Y and z direction dimension is unity. So basically we are saying A equal to 1 is 1 into 1 into A into CV, then del temperature del time, we are writing in this way, into rho into the specific heat, equal to K, and here basically T2 minus T1 divided by delta X, that will be the thermal gradient, conduction gradient, into again the cross-sectional area in Z and Y direction, 1 into 1, and Q dot A is basically the thermal energy that is coming in. So thermal energy that is coming in, the space energy is going up and thermal energy is being conducted. So these three quantities are participating quantities, and from there, just next line following the algebra, we will be able to create 1 plus twice f T1 n plus 1 minus twice f T2 n plus 1. So at n plus 1th level, T1 and T2, these are basically, this quantity on the right hand side, this is alpha, thermal diffusivity, this is heat flux, delta T, delta X, thermal conductivity, all are known, and this is T1 at the initial time level. This is also known. So this can go to the right hand side. First equation then will be 1 plus twice F T1 n plus 1 minus twice F T2 n plus 1 equal to this entire term, which can be evaluated, will be pushed to right hand side. We have exactly done that. 1 plus twice F minus twice F, and this it is coefficient of T1 and this is coefficient of T2. So these two entries are there in coefficient matrix. T1 and T2, these are unknown terms, and this known quantity from this previous equation, this has come here. Now from node number 2 to node number 7, all the equations we can write. Basically this will read as T1 into this quantity plus T2 into this quantity 1 plus twice F plus T3 into this quantity equal to T2n. So all the equations now can be written in terms of coefficient matrix unknown vector equal to known vector. And as we discussed, the last equation should be again boundary condition that T8 is getting involved, but T8 is outside the domain and information is known that it is at initial temperature. So that this is the last equation. Entire right hand side, all the quantities are known, we can evaluate them. T1 to T7 are unknown, and this side F is a known parameter. 1 plus twice F is also, when F is known, this is known quantity, and this is minus F. So this is a tridiagonal matrix. In the coefficient matrix, all the terms are known. Right hand side resultant vector is also known, but this unknown vector is not known, T1 to T7. If we have just discussed Thomas algorithm. If we apply Thomas algorithm, we will be able to solve this. Now I have a request to the participating students that this problem is there, please read it. I have formulated this problem on behalf of you. Try to understand and appreciate this. Then write a code by yourself to solve this problem and find out the result T1 to T7 using Thomas algorithm. So that's all for today. Thank you very much. The class has been extended a little beyond, but if you have paid good attention, you have learned a lot, and with confidence you will be able to apply this in our subsequent exercises. Thank you very much.